Hello. I'd like to introduce our second CI Symposium speaker, David Rubin. He's Associate Professor in Physics and Astronomy Department. He obtained his PhD in 2013 at UC Berkeley. His research spans astronomical surveys, data reduction, especially through precise modeling of data, cosmological analysis, and physical calibration. He's also co-lead for the Supernova project infrastructure team for the hopefully upcoming, Nancy Grace Roman Space Telescope. And he'll be speaking about, his title is Evidence for a New Physics from a Unified Bayesian Supernova Framework. David?
And yeah, I think I've got the talk at the right level, but definitely I know there are a lot of folks online, and so just interrupt in the chat if you have a question or I go through something too quickly. So the talk outline looks like this. We've got some backgrounds. We've got some cosmology background, including perhaps the most important discovery in all of cosmology, that the universe is expanding, some type 1A supernova background. And then we get into the meat. We've got the regression problem that is type 1A supernova cosmology. And then finally, we get to cosmology constraints. So what we're seeing is very strange evidence, some evidence of something very strange that looks like dark energy is evolving in time. So we'll talk about what all of that means. So we start with cosmology. So one of the languages of cosmology is Einstein's theory of general relativity. And so within a few years after Einstein wrote down the theory of general relativity, people started applying this theory to the universe on large scales. And so one of the simplest ways to do that is to assume that the universe is homogeneous and isotropic on large scales, which we call the cosmological principle. It just means there's no special place in the universe and there's no special direction in the universe. So if we found a magnetic field that was running up through the universe, that would be evidence against isotropy. And if we found that the universe on large scales was very lumpy, that would be evidence against homogeneity. So here's what the universe actually does look like on large scales. So this is a set of measurements from the Sloan Digital Sky Survey. So these are measurements with respect to Earth, we are here. And this is going back billions of years. And so you can see that the galaxies cluster. Each of these is a galaxy, and as you get up here, they're quasars. But each of these cluster together. But if you kind of average over large enough scales, you can imagine that you're coming up with something that's pretty homogeneous. It's not going to be perfect, but pretty good. So let's take those assumptions. Let's take general relativity, and let's take isotropy and homogeneity. And we get a few equations, one of which is this one. This is one of the Friedmann equations. And so the idea is that a static universe, and a universe that is eternal and unchanging, actually turns out not to be stable. So I have two widely spaced masses in the universe. Over time, I either expect them to drift apart as the space between them expands, or to come together. Now that's to be very clear that they could be moving through space in addition to that effect. But what I'm talking about really is space itself changing size. So this is perhaps the most important finding in all of cosmology. So we expect the universe to either be expanding or contracting. And so we can try plotting the scale of the universe as a function of time. So here, parameterizing this A of t parameter. So if we set the relative size of the universe to 1 today, we are here, at least we are here now. And then we can plot the expansion going back in time. And so we can get curves like these. And these curves differ by how much matter is in the universe. So if you had a purely empty universe, then the universe would just expand at a constant rate. So let's see, we can probably see that in this equation. So the second derivative in time of the expansion is going to be 0. There's no density in the universe, so we'll just get 0 for the right-hand side. And if we have matter in the universe, then the expansion will decelerate. It's going to slow down. And so now, for many decades, cosmologists thought the question was, well, do we have enough matter in the universe to slow down the expansion and recollapse it? Or maybe the universe will expand forever, but always slowing down. So this is the background to cosmology. Now, how do we figure out what universe we live in? Well, we have to measure distances somehow. So we have actually a very nice relation that we can look at. So imagine that we had a standard candle. So this candle could be, well, type 1A supernova, but it's something where we know their intrinsic luminosity very, very well. So all the candles, if you were looking at them from the same distance, have the same brightness. So the longer the light's been traveling to us, the fainter that candle is going to look. So there's actually only an approximate correspondence between the top axis and the bottom axis. So that's the basic idea. The farther away the candles are, the fainter they're going to look. You can see that I've also made the candles smaller. So standard rulers also serve to measure distances in the universe. We had something where we knew how big it was. We were looking at it from different distances. Then you could also use that for distance. And then there's another effect too, which is general relativity tells us that as the universe expands, it stretches out the wavelengths of light for the light that's traveling. So if light leaves a supernova 8 billion years ago and comes to us, and the universe roughly doubles in scale during that time, then the wavelengths of the supernova double as well. So instead of a blue supernova, like a blue candle like this, we see a red candle. And so what we have here is the distance redshift relation. So this tells us what universe we live in if we go out and measure enough of these things. So these were the first candles to be successfully measured over billions of light years. So these are type 1A supernovae, artist conceptions. We haven't seen one this close, and yeah, it's a good thing. So what we have here is a standard candle, and we think that one reason they're so standard is because they all have very similar progenitor systems. So these are white dwarfs that one way or another accrete matter, and they reach a point, waving over some of the physics here, but they reach a point where they explode. So they undergo, first they start nuclear burning, and then they actually detonate. So there are a couple of scenarios for how a white dwarf can accrete matter. There are a few more than this, but the basic pictures are a single degenerate scenario. So we have a white dwarf there, and we have some other kind of star. So this is a binary star system with white dwarfs are degenerate. So this white dwarf is accreting from its companion, and it reaches a point perhaps where degeneracy pressure can no longer support the white dwarf, and then it explodes. We could also have a double degenerate system where two white dwarfs in spiral and detonate. And of course, nature could do both of these things. Okay, so unfortunately, they're not exactly standard candles, but they are standardizable. So there were two standardization relations that were used even back in the 90s when type 1a supernova cosmology really got going. Two standardization relations that were used. So here we're looking at the absolute luminosity on sort of a log scale that astronomers use. Absolute luminosity as a function of time in days. And so you can see that the supernovae are getting brighter and brighter and brighter over a period of weeks and then fading out. You can see that they are not all the same luminosity, but the less luminous ones decline faster, and they actually also rise faster, although that wasn't immediately apparent. So the decline rates for these more luminous ones are slower. So if you measure that and standardize, then you can make all the supernovae lie more or less on top of each other. Unfortunately, it's not just supernovae in the universe. There's also dust. And so dust makes things fainter and it makes them redder. So here's, I don't know, for a forest fire or something like that. So you've got a lot of particulate matter in the air, and the sun is fainter and it's redder. That is, the blue wavelengths get scattered and the red wavelengths make it through. So we can see this with supernovae as well. So here are two supernovae, the bottom one and the top one. Same sort of plot as that. The bottom one was far less luminous, but you can also see it's way redder. So at blue wavelengths, it's even less luminous than at sort of greenish wavelengths. And so these are two relations that we have to take into account. Now, unfortunately, here's where the complexity is starting to build. You'll see why the regression problem kind of looks like it does. That's not the only reason that supernovae can be red. So this is a measure of dust extinction. So this is a measurement directly based on the supernova color on the x-axis, and on the y-axis, it's a spectral feature that correlates with dust. So there are these diffuse interstellar bands that we observe in the Milky Way and other galaxies, and they tell you something about the amount of dust. And so this is telling you that most of the color variation is coming through dust, but some of it comes from spectral feature variation. So this is now looking at supernova spectra as a function of wavelength. And this is looking at different components of variation. And so this is the calcium feature here and the silicon feature there. There are some other features around. But the point is, not all type 1a supernovae look identical. And so if I make measurements of these, if I take imaging measurements where I'm doing some integral over wavelength ranges, then I'm going to confuse some of my spectral feature variation for extinction. So we need to be careful, and we need to account for multiple types of color in type 1a supernovae. So yeah, this is definitely hopefully sounding like a semi-nasty regression problem. I don't know. So all is well and good for about 15 years of type 1a cosmology. And there was a technique that people used to figure out whether or not things were working, which is host galaxies can be radically different. You could have, these are different stellar masses for host galaxies. So the Milky Way is about here. But you can have massive elliptical galaxies that are old, metal rich, totally done forming stars. You can have galaxies in the middle, like the Milky Way, little starburst galaxies that are rapidly forming stars, tons of dust. And if type 1a supernova luminosity, after standardization, agreed across all of these stellar masses, across all these galactic environments, then it's working. It's reliable. And that was true for a while, until about 2010, when the supernova samples got large enough, hundreds of supernovae, that we started to see that it's not true. So this is residual standardized luminosity as a function of host galaxy mass, stellar mass. And you should be very worried about this plot. We certainly were. So this is telling you that astronomer units, so this is bright, brighter is down. But after standardization, high mass hosted supernovae are brighter than low mass hosted supernovae. So you should be very worried about this, because this is the sort of thing where, how do you know that a supernova that went off 10 billion years ago has the same luminosity if you can't even get this right? So you should be worried. Luckily, we solved it. At least it looks like. Okay, so let's go back to the 90s for a second. So two teams, the High Z team and the Supernova Cosmology Project, made these measurements along with nearby supernovae that give you the full time range here. And the measurements didn't look like any of the curves that I drew. The measurements were too faint for a given amount of redshift. So we need another curve. And so this is an accelerated expansion. And so almost nobody saw this coming. So this is a universe that decelerated for a while and then transitions to acceleration. So not only will it expand forever, but expand faster and faster and faster. So these omegas are the density with respect to critical density, which you don't have to worry about too much, but roughly speaking, the best fit cosmology is 30% matter. Just flipping it around to what we actually measure. So this is how we actually view the data. So 30% matter and about 70% dark energy. So this won the Nobel Prize in Physics in 2011. So what was hinted at first with supernovae was later confirmed with the cosmic microwave background of clustering of matter. And everything was very consistent. So this gives us a puzzle. We've now realized that we don't know what 70% of the universe is made out of. It's actually worse because we also don't know what dark matter is. We don't really know 95% of the universe. But we do know that the simplest model that seems to describe all the data is called lambda cold dark matter. So that's a cosmological constant. So a constant energy density throughout the universe, plus non-relativistic dark matter. There are still questions, though. So even if this picture is correct, it raises a number of issues, such as what's called the coincidence problem. So matter, if I stretch out the universe, dilutes. So I have, I don't know, 2 galaxies or 2 planets. I double the scale of the universe. Well, now that I have 1/8 the density of planets. But cosmological constant doesn't do that. It's just a constant vacuum energy density. So why are they equal today? What's special about now? So roughly equal. So we've observed, depending on what you call directly observed, we've observed, at least billions, and probably we have pretty good evidence for, another 15 orders of magnitude than that expansion in the universe. So we've directly seen evidence for a huge range in density variation. But today, somehow, these two quantities came out to be about the same. So that's very strange. But the general goal is to test this model and see if we can break it. Fortunately, we've got this nice Moore's law growth of the data. So starting out with the original papers, we've doubled the supernova sample about every 4 years. We expect this to continue going, as I'll tell you. Here's the current data. Can't really see anything, but all of these are supernova light curves. They're all getting brighter and then fainter. Here's another way to look at it. So we have numbers of supernovae. So now we're up to more than 2,000 supernovae in about 24 different surveys. And what you can see, unfortunately, is that there's no one supernova survey that spans the whole range and distance that we want to look at. So we have to combine those supernovae. And so we have to make sure that we standardize to the extent that we can. So if this survey measures a supernova magnitude, it should agree with that survey on average. And we have to do a bunch of work on that. And we have to there are about 500 systematics terms in the model describing different ways that the surveys might be wrong. And we have to marginalize over all of those. So there's quite a bit of work that goes into that, but we'll gloss over it. So what I'd like to do is start talking about the actual supernova analysis. So one big divide in the field is caused by this selection effect. So real supernova surveys cannot measure every supernova in the universe. They only measure ones bright enough for them to see. So we have a range in distance, and then we've got another sort of that log scale that astronomers like. And then I also plotted the supernova color there. And so you can see we're getting, especially for the red supernovae, they disappear. We can't see them anymore. For the blue supernovae, we can see them farther. But this gives us all sorts of sort of nasty biases in the data. And so we get to the Great Divide. There's sort of a classical technique that was used for a long time, still is used, which is we simulate and remove those biases. So you need to build a simulation, so different observing conditions and the sensitivity of the telescope and the efficiency of following up the supernovae with other instruments, and just we try to build a big simulation of all of that. For every supernova sample in the analysis, you look at how biased your sims are, you subtract that bias from the data. So that gives you a per supernova distance. You do variations on that until you think you've gotten all of the systematics. You put that into a covariance matrix. So this is sort of the first earliest method, but it's still used today. For doing supernova cosmology. So you do simulations and you debias. But what I do, at least what I do for the last 10 years, is Bayesian hierarchical models. So the idea is this is now a regression problem. So it turns out that you can solve for this sort of effect by writing down all of the parameters for the events you've observed and all of the parameters for the events you haven't observed. So this is a generally applicable technique. So then you have to marginalize over everything that you didn't observe. Sounds like it shouldn't work, but it actually does. In theory, a Bayesian model like this, that's marginalizing over everything all at the same time, should give more accurate uncertainties. An open question whether or not that's true, but I think it is. And you can also do things in a Bayesian analysis like have uncertainties that you don't completely know. You can have uncertainty on your uncertainties. That's allowed. So this is, the basis of my Unified Nonlinear Inference for Type 1A cosmology Unity framework. So this is one of the probabilistic graphical models, or actually a slightly older version of Unity, but it is a Bayesian hierarchical model that attempts to solve this problem. In addition, we validate anytime we change the model in any way, we try to validate those changes on simulated data, which I'll talk about a bit later. So again, you can't make a model like this that perfectly represents the actual universe, but the goal is to have a useful model that does at least as well as others. So there's this nice quote, all models are wrong. Okay, so what have I been up to recently with it? So it turns out that there's evidence that there are two types of type 1A supernovae. You may wonder if that's single degenerate and double degenerate. Probably that's a fair amount of what's going on. Yeah. But there's one where they are faster time scale. I know I'm not plotting the light curves here, but faster time scale, and one that's slower time scale. And for any given supernova, you might not actually be able to tell which of these it's in. So that again sounds like something to marginalize over. So a Bayesian model can do that marginalization. So how are we going to build our Bayesian model? So we've got to marginalize now over thousands of parameters. So we have 3 parameters for every supernova. The latent value of the dust, the intrinsic supernova color, and then the light curve shape parameter. Then we also have which mode it's in. And yeah, we also have to marginalize over everything that's not in our sample. But it turns out that this is computationally feasible. And so we use this package STAN, named after Stanislaw Ulam there, who did, I guess, the first Monte Carlo in physics, neutron transport. Okay, so STAN sets up this inference problem as a physics problem, which is always fun. So let's say you have some posterior distribution like this, and I want to draw MCMC samples out of it. And, you know, let's also say that this is in thousands of dimensions of parameter space. So, you know, you could do a few things. You could do Metropolis Hastings random walk, but it's going to take you a long time to walk from one side to the other, potentially. You can do Gibbs sampling, but again, you're sort of bouncing around. It's going to take you a while to make it over. But physics knows how to make it over. Physics says you can use momentum. So we simulate the dynamics of a particle moving through this space. Oh, that's nice, it's looping. Yeah, so you can use momentum and you can get momentum along this path. And so the idea is you write down the log posterior as though it's the potential energy in a Hamiltonian, and then Hamilton's equations here tell you how to move. Unfortunately, as opposed to something like Metropolis Hastings, the Hamilton's equations have gradients in them. You have to get partial derivatives, and that ends up costing most of the CPU time. So you have to take thousands of derivatives for this model just to move this one time step. So I can talk more about STAN if you'd like. This might be the part of the talk that's most interesting for you. So we get out of STAN about 100 samples per core hour. I'll show you the uncertainty budget at the end, but to get that uncertainty budget, we sampled 1 million times. So, and then we had to do multiple variants of different cosmological models, different versions of the data. It adds up. For the simulated data testing, I did 100 realizations, but I only pulled 10,000 samples. And yeah, if you want simulated data that's about the same size as the real data, then you also have to fit a lot of likelihoods too. So this was also quite computationally challenging, but Koa was really essential. So this would have been very hard to do on something like NERSC. I mean, one of the advantages isn't just the CPU hours, but the responsiveness. Like, I can try a variant, I can have some idea, and maybe I just pull, you know, a few hundred samples out or something, so it just takes a few hours, but my job's starting. So the responsiveness, in addition to just the overall amount of computing, is really critical. A lot of this is embarrassingly parallel, so that's great. So for example, we run semi-arbitrarily 2,500 samples per chain, so that they take about a day. So you can run 400 in parallel. But that is not going to scale. So future data sets, as I said, are going to get larger and larger and larger. And so the chains are at some point either going to have to get parallelized or moved onto GPUs. So something like the Cairo can do this sort of MCMC sampling on GPUs. So something like that is going to be where this goes. Okay, so we did this. What happened? This is fraction of the universe. It's that fraction of the critical density in matter. So the cosmological constraints actually don't change that much. It's less than 1 sigma in terms of the uncertainty. So it's encouraging. We weren't too far off in the past. The uncertainties shrink, not dramatically, but they do. That's a good sign. And then we've got this host galaxy luminosity correlation that goes from non-zero to 0 when we do this in the model. So the thing that's been worrying us for 15 years may be solved. There may just be 2 different types of type A supernovae, plus it turns out that there are different populations of dust in different galaxies, and you have to take that into account too. But this is, I don't know, probably the most encouraging result anyone's gotten in 15 years on this. So here's how it makes the host mass correlation go away. So this is the fraction of supernovae that live in massive host galaxies. And so you can see this is the slow mode. These tend to live in lower mass galaxies. And the faster mode tends to live only in very massive galaxies. Interestingly, this is pretty similar to the situation for supernovae back, let's say in 1980. So I keep calling them type 1a supernovae. They used to just be called type 1 supernovae. They were supernovae that didn't show any hydrogen because these are carbon-oxygen white dwarfs. And people were thinking about them as standard candles for a while, but every once in a while, they would find a type 1 supernova that was anomalously faint, way fainter than it had, like a factor of 10 fainter than it had any right to be. And what they realized in the mid-80s is that there's actually type 1a supernovae and type 1 BC supernovae. And the 1 BCs also don't have hydrogen, but it's a totally different explosion mechanism. It's the death of a massive star, or at least moderately massive star, rather than a white dwarf. So totally different physics. And so now, in some sense, we're splitting it again. We're saying that it's not type 1a supernovae, it's type 1a fast and 1a slow, or something like that. Maybe that's double degenerate and single degenerate. It's possible. So yeah, Unity can model all of this stuff. You have to take it into account. So this is the amount of dust extinction inferred up here, and the true color of this sort of intrinsic color of the supernova down here. And this is the probability of being a slow supernova. So yes, these are slow supernovae, these are fast supernovae. And you can see there are all sorts of differences here. So for example, the intrinsic colors are offset a little bit. There are overlapping distributions, but they are a little bit offset. So this is really what you want a Bayesian model for, is when you have overlapping distributions, you need to marginalize over which distribution you live in. Okay, how do we know that any of this works? Okay, we did test on simulated data, but we can also look at predictive posteriors. So this is another nice technique for nice computational inference technique. So the idea is we have these MCMC samples for what we think the right model parameters are. And now we can take those samples and simulate data sets, assuming those really are the right parameters. And so we can look at whether or not the simulated data look like our real data. And they pretty much do. So this is a linear combination of light curve shape and color parameters and magnitude. This is versus light curve shape. These are relatively nearby supernovae. These are relatively distant supernovae. And it looks pretty good. So the blue dots are the simulations from the model, and the red dots are the actual data. And they match pretty well. They might not, I'm trying to stand in front of the part that doesn't look as good. The very fastest declining supernovae might still be a little faint after standardization. So the very fastest, there are equal numbers of supernovae in all of these bins. So the fastest fraction might still be a little understandardized, actually. So it's possible we should go to 3 modes or something like that. We did actually test that, and it doesn't make too much of a difference on cosmology, but something to watch out for. So this is like a cross-check of everything. Did we standardize correctly? Are our modes right? Did we get selection effects right? Because, you know, these really fast ones, they're not very luminous. They have huge biases. They're the hardest ones to find and follow. They're a very biased sample. These are nice and luminous. They're bright. They're less biased. So this is like a pretty good end-to-end test of everything. So I can show you lots of predictive posterior figures. If this gives you a sense of what's going on. Here's the same thing as a function of color. Also looks good. So now we get to the fun part, cosmology. So I told you about the inference and type 1a supernovae and modeling them. So what did we learn? Well, we learned something strange. So we go back to that. I went over it a little quickly, but the equation of state parameter on the second slide or something. So the ratio of the pressure to the energy density for dark energy. And for a cosmological constant, its pressure is actually -1 times its energy density. So a cosmological constant would be at -1, and then it wouldn't vary with time. So this time variation would be 0. So -1, 0 is the standard concordance cosmological model. And what we see seems to have some tension with that. So this is supernovae plus distribution of matter plus cosmic microwave background. This is pulling it apart. This is doing basically a leave one out test. Baryon acoustic oscillations, distribution of matter and cosmic microwave background also show tension in the same way, leaving out supernovae, supernovae plus C and D, supernovae plus baryon acoustic oscillations. They're all consistent with each other. You can even look at the supernova only constraints, although that, the more data you remove from this, the larger the uncertainties get. But everything seems to be consistent. It's just not consistent with the standard cosmological model. It's consistent with something over there. So we can poke at the data. We can try to see what's causing that. So roughly speaking, this would be the expected cosmological model. So 30% of the universe in matter, dark energy equation of state, -1 for all time. And then here's one that's basically near the best fit. So it's time varying dark energy. So this red curve. And, that's a compelling fit to the data. It's not conclusive. You wouldn't say from supernovae alone that that's it, but it's certainly a compelling fit to the data. Here's the same thing for baryon acoustic oscillations. So you can measure different combinations of distances, looking at how galaxies cluster. And this is the expected results. This gray band, and there are actually now 2 data releases from these folks. Data release 2 includes data release 1. That's why the uncertainties are smaller. And yeah, you can see some tension with the standard cosmological model, a little bit of tension, a little bit of tension. It's not conclusive, maybe a little bit of tension here. It's certainly not conclusive, it is suggestive. And it is interesting that supernovae and BAO are telling you something that looks very similar. So between the DESI results, between the baryon acoustic oscillation results, some other supernova results from the dark energy survey, and then my results with Union 3, we've gotten quite a lot of attention about this. So it's been a lot of fun. I was actually telling people about our results at a conference when DESI announced their results, which confirmed it. So it is, yeah, it's been quite a lot of fun. But it's kind of a weird part of parameter space, actually. So, yeah, what did this mean? So, same axes we were looking at before. And so here's some data combinations. And then here's some theoretical models that might explain it. So one of the first things that people tried when the acceleration was found in the 90s is, could a scalar field be driving the acceleration. So a scalar field is a field where it's got a value but no direction everywhere in the universe. We think scalar fields might play a role in the very early universe. Higgs is a scalar field. So people try to play with, well, can a scalar field do this? And the answer is not quite. Scalar fields tend not to give you evolution with time that's as dramatic as what we're seeing. So you can get some kind of improvement, but it doesn't quite bring you down to where the data are. So these are different different potentials for the scalar field. Okay, so there's not an obvious way to do this with the scalar field. Could we modify gravity in some way? Maybe. It's hard. It's really hard these days to modify gravity. General relativity has a lot of check marks in its column. You know, the gravitational waves, the motion of planets in spacecraft in our solar system. Yeah, it's tough to beat general relativity. Taking pictures of black holes and, you know, they look as expected, you know, it's tough to beat general relativity. But maybe there's something there. Non-cold dark matter is an interesting suggestion. You could maybe do something with dark matter, not dark energy, that would look like our results. Could be something else. I wonder if we're just getting some significant part of our cosmological model wrong, something that we thought was nailed down that isn't. Okay, really quickly, we can look at the uncertainty analysis. So this is kind of an uncertainty analysis unlike any other. So